So I'm going to be going over Coulomb's law and the net force acting on a charged particle. So there are three parts to these problems that you can see listed below. So depending on which part you kind of struggled with, if you have the checklist with you, whether it was drawing just the force diagram, calculating the individual forces, or the net force, you can jump ahead to that specific part in the video. If you kind of have trouble with everything or just want to hear kind of a refresher with all of it, you can just watch the whole video. It's only about 7 minutes long. So the first thing we have to do with each of these problems is start by drawing the force diagram. So in this problem we're going to look at charge 1, and we need to determine the net force acting on charge 1. So the first thing I need to do is draw my force diagram based on attraction, repulsion, and those principles there. So charge 1 and charge 2, if we start there, if you notice, so charge 1 up here is positively charged, charge 2 is negative. So charge 2 is going to attract charge 1. And remember, we are worried about where charge 1 is going to go. So in this situation, use the laser pointer, charge 1 right here is attracted to charge 2, so it is going to move towards charge 2. So that's the direction I need to draw my force vector. So you can say force of 2 on 1. You can just say force of 2 just so you know that you're talking about force 2 there. So if I do the same thing now for charge 3, so again charge 1 kind of here, charge 3 is going to repel charge 1, so it's going to push 1 to the right as well. So therefore I can add this, another force vector down here, so the force of 3 on 1, so both of those are acting to the right. Now, even though charge 4 over here is outside of charge 2, charge 4 is still going to have some attraction between charge 1. So charge 1 is positive, charge 4 is also positive, so therefore charge 4 is also going to repel charge 1, but it's going to repel it and push it to the left because Q1 is going to move away from Q4 if it was just those two charges. So I can start here. So the force of 4 on 1, which is how I would draw the force diagram. So we're concerned about where is charge 1 going to go in these situations. And wherever it would go, if it was just those two charges, that's the direction I need to draw the force vector. So if it was just 1 and 2, charge 1 would move to the right. If it was just 1 and 3, it would move to the right. And if it was just 1 and 4, it would move to the left, which is where we see our force vectors. Now, calculating the individual forces is just where we're going to use Coulomb's law. So remember, Coulomb's law is the equation you'll always be given. So we have to just calculate this for each individual force. So I'm going to start with force 2 on 1. So I already have it written down here. So the electrical force, remember, is equal to Coulomb's constant. So K Q1 times Q2 over R squared. So those are the values I would use there. So remember, K is always 9 times 10 to the 9th. Q1 in this case is 4.9 times 10 to the negative 6th. And Q2 is 3.5 times 10 to the negative 6th. And my separation distance for 1 and 2 is 0.1, with the radius distance between them. And remember, we need to square that. So a couple of things with how I set this up. So we're looking at charges 1 and 2. 1 and 2 up here. So first thing, 9 times 10 to the 9th. 4.9 times 10 to the negative 6th. And 3.5 times 10 to the negative 6. If you notice on this one specifically, the charge of 2, I dropped the negative sign because negatives have no, positive and negative has no importance here except for the fact it would tell us that the charges were either oppositely charged or they had the same charge for a positive answer, which that doesn't matter to us because based on our force diagram, that's how we're going to determine direction. Negative doesn't necessarily mean to the right. or to the left. Positive doesn't mean to the right or to the left, because here we would, if we use the negative, we get a negative answer. However, we mean moving to the right, which wouldn't kind of fit into the way we've looked at it before. So we drop the signs and simply just look at everything as positive numbers, and we'll set the direction of the charge based on our force diagram here. So in this case, once we calculate this, which I'm going to switch to the next slide to show that. So here is charge 2. So this would be charge 2. It's acting to the right, so I just set that. So I do that calculation. Down here, I'm going to label these as well. So this would be 2, this would be 3, and this would be 4. Charge 3 has a force of 2.47. So if I do that calculation again, which in this case it was already positive, so I left it. And then down here for charge 4, it acts to the left, so I can say that it acts to the left. So given those calculations, how I would set those up, and just to get those actual numbers. Then I need to calculate the net force. So the net force, again, here are my values from before. I have force of 2, I have the force of 3, which also acts in the same direction, and I have the force of 4. You can do this a couple different ways, but the easiest way kind of right now is if we look at this, like look back at your force diagram, that's how we're going to determine this. So everything acting to the right, how does it compare to everything acting on the left? Which one's bigger? Are they the same? How are we going to calculate this? So just by looking, I can see that the force of 2 is 15 newtons right here. Force of 3 is 2.47. This is clearly more force acting to the right than is acting to the left down here with just the force of 4. So if I actually wanted to total that up, here I would get, on this side, I would have 17.91 newtons acting to the right, and I would have just 6.62 acting to the left. So, based on that, I can tell that the net force is just going to be how unbalanced is the force diagram. So remember, just net force means how unbalanced is our force diagram. So in this case, the unbalance would be the difference between these two numbers here. So 17.91 minus 6.62, which would be 11.29 newtons. And I'm going to say to the right because the right force is bigger. The right side of the force diagram is larger, so therefore the net force is going to act in that direction. So again, all positive numbers from our calculations, and then we can just set directions down here based on that. We can just add everything up on this side. How does it compare everything on this side? And find the difference. Now, if everything was acting to the right or everything was acting to the left, I can just add them. But since I have some acting in both directions, I have to take both sides of that for an answer of 11.29 newtons to the right.